Welcome to massive open online course on fluid flow operations. In the previous lecture, we have discussed something about velocity distribution in laminar flow and how the flow is flowing when there will be a plate over this fluid moving in the same and opposite directions, and what will be the Poiseuille's flow, what will be the Courtine flow, and what are the different phenomena of the fluid flow whenever it will be moving through the pipe, and fluid will be viscous in this case. So, how the velocity of the fluid will be showing based on the governing equation like Navier-Stokes equation, even other phenomena also we have discussed. Now, in this lecture we will discuss the velocity distribution of turbulent flow for this viscous fluid. Now, if we go back, that what is that viscous flow? That viscous flow is the ideal fluid which is non-viscous. In that case, we cannot consider that it will be ideal if it is there is a viscous phenomena there. And for ideal flow, I think we have no viscosity. In that case, we will be calling as that the ideal flow, ideal fluid, and the flow is called ideal flow. And also the ideal fluid assumptions we have derived and discussed the basic equations of the flow. And we also know that in the nature there will be no practical fluid that has zero viscosity. So, all the fluids in the nature will be considered as the viscous flow, and the flow of that viscous fluid is called the viscous fluid, and all the viscous fluid will be flowing as a turbulent flow, and also as some extent it will be laminar flow if there is a higher viscosity, and that depends on the velocity of the fluid and also geometry of the conduit through which the fluid will be flowing. And also the fluid having viscosity that are known as practical or real fluids, those who have that viscosity, and the flow of that real fluids is known as the practical or viscous flow. And we have also discussed that due to this viscosity, the real fluids of course differ from the non-viscous ideal fluids, because their governing equations that will be different. And also we have discussed that energy balance equation, where that for ideal flow there will be no head loss is there, but in the viscous flow there will be friction, and because of which there will be some head loss, and because of that conservation of energy you will be able to that what will be the head loss there because of this friction and because of this viscous flow. And viscous flow of course will offer that frictional or shearing resistance to the motion of the fluid. We will be discussing again that what will be the universal resistance or universal resistance law there in the that is forthcoming lecture. And also a continuous supply of energy is required to overcome this shearing resistance whenever this viscous fluid will be flowing through the conduit. And we have discussed that Navier-Stokes equation, laminar flow through the gap of two flat plate, Poiseuille's flow, Courtine flow, laminar flow through the pipe and annular pipe also. So, in this lecture we will be discussing that what will be the turbulent flow and what will be the different characteristics feature of turbulent flow. So, in this case Reynolds number, if it goes beyond a certain value, we will be considering the flow will be as turbulent flow. We have already discussed in the earlier lecture also there will be a classification of this laminar flow and turbulent flow based on the Reynolds number, and in that case if Reynolds number is less than 2300, that is for circular pipe flow, in that case we are getting the laminar flow, and if this Reynolds number is greater than 4000 and it will be called as turbulent flow. So, in that case in the turbulent flow sufficiently strong turbulence will be resulted based on this high velocity, and because of which there will be a Reynolds number high enough. And also the phenomena of turbulent motion is called the turbulence is there. So, we will be having the, what will be the degree of turbulence, we will be having the degree of turbulence and as well as the magnitude of the turbulence is there, and based on this velocity, and the fluid motion is irregular, and in this case it will be chaotic. Please see this picture there. In this picture it will see that there is a chaotic nature of the fluid flow, and it will be called as turbulent flow. And also whenever any ship is moving on the surface of the any river or sea, there behind this ship, how this actually the fluid particles will be getting turbulence because of that impeller velocity and impeller rotation, and how fluid particles as a parcels it will be displacing from its mainstream there. So, based on which this turbulence will be creating there. And there is a complete mixing of the fluid also during this turbulence. Of course, whenever we are just pouring some liquid in a suppose in a cup of different types of liquid, and there you will see because of that jet energy, the liquid will be making turbulence inside the pan of the other liquid there. So, in that case the mixing of the fluid will be there, and that depends on the how you are that supplying the liquid and what will be the velocity of that liquid in that particular operation there. And also emergence of strong vortices also will be there in the turbulence flow, and you will see some eddies also will be forming whenever a fluid will be flowing through the pipe. Whenever it will be getting some disturbance, at the point of disturbance you will see the fluid particles will be getting distorted, and also it will be deviating from its or it will be just changing its position from the mainstream, and haphazardly and in the chaotic in nature, so that the strong vortices and eddies will be forming there. And in that case you cannot expect that there will be laminar flow. Of course, a high shear will be produced, and because of which there will be a phenomena that is called degree of turbulence will be creating. And other thing is that the velocity distribution in that case near the boundary will be quite large compared to the laminar flow, and the flatness of the velocity distribution curve will be there, and this is because of the mixing of the fluid layers and exchange of momentum. And also we also derived that in the laminar flow the average velocity is half of the maximum velocity, and whereas in the turbulent flow you cannot expect it will be half, it may be more than half, and then it will be up to I think 0.85 this average velocity to the maximum velocity. And also the velocity distribution is you will get it will not be just in case of what is that we got for laminar flow it will be paraboloid, but in this case for turbulent flow this velocity distribution will follow the power law, or what is called, it is called logarithmic flow or logarithmic law in turbulent motion. So, here in this picture you will see that nature of the distribution of the velocity here in this case for laminar flow you are getting this type of paraboloid velocity distribution profile, whereas in the turbulent flow you are getting this type of velocity profile. So, you will get two types of profile for velocity distribution, one is for smooth pipe and another is for rough pipe. You will see for rough pipe it will be like this, here it is shown, and whereas for a smooth pipe it will be more flat compared to that what is that rough pipe. So, in that case you will see the viscosity nature also will be different, and also there will be some friction, the nature of the friction will be different in the case of rough pipe compared to the smooth pipe there, and that depends on the roughness of the pipe. Now, in this case you will see that during this turbulent flow there will be some irregular and random motion of the fluid particles, and for two dimensional flow you will see the instantaneous velocity of the fluid particles in turbulent flow condition can be expressed by this u will be equals to u dashed plus u bar. Now, this u bar is called the time average mean velocity, whereas u dash is called fluctuating velocities. Whereas in the y direction this v will be equal to v dash plus v bar, whereas this v bar is called that average mean velocity in the y direction, and v dash is called the fluctuating velocities in this y direction. Similarly, in the z direction w will be equal to w bar plus w dash, and what should be the pressure components also similarly you can consider in the turbulent flow, that P should be P bar plus P dash here. So, in this case bar should be considered as a time average mean velocity, where a dash is considered as a fluctuating velocity. So, whenever we are observing any turbulent flow, you can say that velocity components will be such like that one should be the fluctuating components of the velocity there, because this the fluid particles will not follow the regular fashion to flow in a conduit. So, its path will be a zigzag way, so that in each point its that is tangent or streamline coefficients will be different, and also because of this you will see the nature of the mixing of this fluid, there will be different compared to the laminar flow. And in that case, if we are having that different components in x, y and z direction, these velocity fluctuations because of this turbulence, and in that case you have to consider this fluctuating components of the velocity. Now, if you are getting the average or mean of these fluctuating components, and if you are considering that velocity as a u bar here, so it will be like this. So, this will be time average velocity. Now, this time average you have to consider this time is sufficiently enough, so that you will be having more accurate, that means actual velocity to consider or to analyze the velocity distribution in the turbulent flow. And also these fluctuating components you can measure by hot wire anemometer to get this fluctuating velocity, as shown in this figure. You can record by this hot wire anemometer to observe this fluctuation, and after that you have to take it time average, so that for further analysis you can get these other properties of the turbulent flow. Now, what will be the definition of the time average velocity and that pressure? Now, time average velocity will be like this, it will be defined like this, here 1 by t into 0 to t integration of this u t into d t. So, here in this case capital T is denoted by time range here 0 to maybe infinite time also you can take, that is up to you, that it should be a sufficiently large interval of time, so that you can get more accurate results to analyze. And also in the v directions it will be the like similarly time average in the y direction, in the z direction it will be like this, and also pressure average pressure will be again the time average, because in this case whenever you are going to measure the pressure by pressure transducer by sophisticated instruments, they are the pressure transducer will give you the force difference by the resistance like voltage resistance. In that case you have to calibrate it, and you will get the pressure and fluctuating pressure, and with respect to time it will be there, and after that you have to get the time average velocity of that resistance of the flow, and from which after calibration you can get the actual pressure components there. Similarly, what will be the fluctuating components, average fluctuating components to be also considered by the time average component here. So, you are here also you have to define that velocity fluctuating components in the x direction as u dash, which will be 1 by t into 0 to t integration of these components here by this. Similarly, in the y direction you have to calculate these velocity components by taking time average of these. Similarly, in the z direction, and also what will be the fluctuating pressure components also will be taken care by taking the mean of this time average. So, in that case we have to then consider for further analysis by taking this time average velocity and pressure. Now, what should be the magnitude and intensity of the turbulence there? Now, magnitude of the turbulence will be defined as the arithmetic mean of root mean square value of turbulent fluctuation, and it is defined and it is given in equation number 3 how it will be there. So, you have to sum of these fluctuating components, the square of these fluctuating components, and then divided by 3, that is mean value, and then after that you have to take the square root of this, then you will get the magnitude of the turbulence. And what should be the intensity of the turbulence? It is also that the average velocity mean of root mean square value of the turbulence here. What should be the root mean here? Magnitude of the turbulence, then you have to taking the average based on this summation of this average velocity in x, y and z direction. So, by equation number 4 you will be able to calculate what should be the intensity of the turbulence. If you know the velocity components in x, y and z direction and the average velocity, then easily to calculate what should be the intensity of the turbulence and also magnitude of the turbulence there. Now, another important theory to be discussed for the turbulence flow, that is called Boussinesq's eddy viscosity theory. Now, in this case the shearing stress, in the laminar case also we have discussed the shearing stress. So, in the turbulent flow what should be the shearing stress? So, in this case the shearing stress of this turbulent flow is the sum of this laminar flow shearing stress and also shearing stress due to the eddy movement in this turbulent flow because of the viscous effect and also what will be the roughness of the pipe there. So, because of which you will get the shear stress will be something different from the laminar flow. So, what should be the shear stress in the laminar flow? What will be the shear stress in case of eddy producing because of this turbulent flow? So, you have to sum up this two shear stress. So, it will be called as total shear stress in this turbulent flow. So, that will be defined as what is the turbulent flow. In the turbulent flow the shear stress will be mu e into du by dy, whereas in the laminar flow it will be mu l into du by dy. Mu l for laminar and E for eddies here. Eddy it is coming only for this turbulent flow there. So, you have to sum up these two components to get the total shear stress for turbulent flow. So, it will be here this way. Only thing is that viscosity of eddy to be considered here instead of what is that laminar flow. So, in the laminar flow we got this mu L, that is Newton's viscosity, Newton's law of viscosity, based on which we are defining that shear stress in the laminar flow as mu L into du by dy, whereas in the eddy viscosity we are defining another viscosity coefficient. It is called eddy viscosity or eddy viscosity coefficient mu e, and it will be later on will be discussed also how it will be defined for that. Now, so as per Boussinesq's eddy viscosity, we can say that the summation of these two shear stress of laminar and eddy will be considered to get the total shearing effect of the turbulent flow. And the shearing stress in the turbulent flow, if we consider that two parallel flat plates, then how this velocity distribution will be there and how this shear stress will be considered in that case. So, if we consider this flow between two parallel flat plates at velocity u in the x direction, as u will be equal to u bar plus u dash, since it is a turbulent flow. So, we have to consider this average time average mean velocity, that is u dash u bar and u dash also fluctuating components. And whenever you are considering the x direction, then in that case only v will be equal to v dash, only that fluctuating components in the y direction to be considered. And the Reynolds stress in that case in the laminar flow, in the case of laminar flow will be defined as tau L will be equal to mu into du by dy. And the shearing stress in the turbulent flow will be defined the summation of these two, that is laminar and turbulent, that we have already discussed. So, it will be here as equation 7 how this shearing stress in the turbulent flow only to be considered. Now, important point here that mu e whatever we have discussed here, see the mu is called the turbulent eddy viscosity. It is not the value of the physical property that depend on the temperature or such, but a quantity fluctuating according to the flow conditions. So, you have to remember it is not the turbulent, it is not the physical property, but it is a phenomena that depends on the temperature, and also so it is not the temperature, but it is a quantity that according to the flow condition to be defined here. And also in this case you will see if we see the shear stress distribution here, how this turbulent flow in this case it will be there. So, this is the components of the turbulent flow, this is the components of the dashed line is considered as a turbulent flow shear stress distribution, whereas the firm line is considered as the laminar flow shear stress distribution. So, this shear stress is called the Reynolds stress here for the turbulent flow, and Reynolds stress in the turbulent laminar flow it will be considered as this. And in this case Prandtl's given a widely accepted theory to analyze the velocity components based on the mixing length of the fluid layer whenever it will be flowing through the conduit. So, in that case Prandtl's given the theory based on the concept of momentum exchange between the layers of fluid in turbulent flow, and he actually correlated the fluctuating velocity in the turbulent flow by considering the assimilation, or you can say that mixing of a rotating parcels of fluid whenever it will be flowing. See here in this video there how fluid particles are having mixing in that case the rotating parcels of the fluid of turbulent flow with the character of the other fluid parcels by collision with them, how it will make this eddies there, and these parcels of fluid particles it is called the eddies, and during the flow whenever it will get the obstructions over any object, then beyond this object you will see the streamline how it will be broken down, and it will be circulating, and because of the energy distribution over there, and then how this fluid particles getting mixing intermixing by just breaking the breaking this what is that streamline of these fluid particles there. And so, in this case we can say that whenever there will be assimilation, then the assimilation length traveled by the eddies will be considered as mixing length here. So, which will be denoted by L. So, in this picture also you will see that if there is a flow, what will happen, the fluid layer will be having layer 1, layer 2, layer 3, and you will see what will be the length between these two layers, layer 1 and layer 2, it will be considered as the mixing length here. So, considering the separate length of two layers, it will be called as mixing length, and then these fluctuating components, that is fluctuating velocities in the x or y direction, how it is correlated with this mixing length, and also the velocity gradient that is given by this Prandtl here. So, it is called Prandtl mixing length theory. So, u dashed that will be equivalent to v dashed, that will be equal to L into that is what is called du by dy. So, this velocity component, fluctuating components is related to the shear called shear strain. So, this shear strain or you can say shear rate here. So, the proportionality constant is considered as a mixing length. So, this mixing length is nothing but the separated length of the two layers whenever fluid will be flowing as a streamline there. So, at higher velocity you will see that streamline will be broken down, and then there will be a gradient of this velocity, and that velocity gradient will give you how these fluctuating components will be estimated there. So, in this case you will see, if you consider that u dashed and v dashed, that is velocity fluctuating component in the x and y direction, and if you are plotting this, you will see they will be almost same. Here in this case has a large probability of being negative also there, both these. So, and because of this you will see Reynolds stress will be defined as that rho into minus rho into u dashed v dashed. So, we will come to that point. Now, how this Reynolds stress then to be actually estimated or to be analyzed here. Now, if we consider that u dashed bar, that is average fluctuating components in the x direction, and it will be the difference in the time average velocity of the two layers separated by distance. Here in the figure it is shown. It is called the mixing length through which the exchange of the momentum happens. So, in that case if we consider that these two layers, now what should be the mass of fluid that transported vertically with its original momentum from one layer to the another layer, and how the momentum can be gained in the later layer due to the fluctuations. And in this case you have to know the average velocity for the other directions also. There velocity components in the other directions like y directions, then if it is considered as v dashed bar, then in the layer 1, then momentum difference between these two layers of 1 and 2 can be considered as rho v dashed into delta A into u bar minus u plus u dashed bar. Here you just see, consider here this is the average velocity, and in this case this is the what is that velocity fluctuating components u dashed. So, this in this case in this layer the velocity is u bar plus u dashed, and here in this layer the velocity is u. So, what will be the difference between these two layer? What will be the velocity difference? This is simply u dashed, that is velocity fluctuating components in the x direction. And then what will be the momentum is there? Momentum it will be equal to rho into v dashed into A, that means mass is rho into v dashed into what is that delta A. It is your what is that in the y direction, what will be the volume. So, this volume flow rate into density, it will be coming as mass. So, mass into here u, that will be your momentum here. What is the u? That means, what is the difference of velocity between two layers. So, it will be considered as the momentum change. So, this total momentum change will be rho into v dashed into delta A into u bar minus u dashed plus u dashed bar. So, finally, if it is the momentum, then what will be the shear stress? Then momentum divided by cross sectional area, then it will be considered as the stress. So, this is called that Reynolds stress. This Reynolds stress, then finally, you are getting that minus of rho u dashed v dashed bar. So, Reynolds stress will be actually taken as the momentum change whenever in the turbulent flow liquid layer having velocity difference based on the fluctuating component there. So, we can calculate what will be the momentum exchange between two layers by this deviation of the velocity, and also in the y direction if there is a velocity component, fluctuating component as v dash. So, in the y direction if we consider that velocity and also cross sectional area is delta A. So, we are having this that is volume, then rho into volume, that will be mass, into then what will be the in the x direction, what will be the what is that deviating that is velocity, that is called fluctuating components. So, if we multiply this, we are getting the momentum exchange, and by divided by cross sectional area we can get the Reynolds stress there. Now, as per Prandtl's mixing theory, what should be the Reynolds stress then? Now, if we substitute the fluctuating components of velocity from equation number 8, that the here the fluctuating components are defined by this L into du by dy given by the Prandtls. So, as per this Prandtl mixing theory, if I substitute this velocity fluctuating components here, then we are having this tau Reynolds, that means Reynolds stress will be equal to rho L square, this one rho L square into du by dy whole square. So, this is your Reynolds stress based on this Prandtl mixing theory. Now, if I consider that Reynolds mixing length is there, and what should be the relation between this Reynolds stress and the mixing length, then we can get by this equation number 10 there Reynolds stress. So, the relation is called the Prandtl's hypothesis or mixing length, which is widely used for computing the turbulence shearing stress here. And in this case, remember that mixing length L is not the value of a physical property, but a fluctuating quantity that depending on the velocity gradient and the distance from the wall. So, you have to remember this. So, very simple that you have to remember this Reynolds stress as minus rho u dashed v dashed, and based on this Prandtl mixing length theory, if you substitute that u dashed and v dashed, you can get rho L square du by dy whole square. So, this one is very important for computing the turbulence shearing stress for any chemical engineering operation or by simulation of the process there in the turbulent flow condition. Now, it is very difficult to actually calculate or estimate this mixing length by what is that, by substituted instruments, what would be the distance between two layers. So, in that case Prandtl or some other investigators, they have estimated this mixing length by experiment by relating to other components by indirect way. So, they have given different correlations. So, what should be that correlation? So, mixing length we know that it will be not the physical property, but it is a fluctuating quantity which will be measured or estimated by what is that velocity gradient and the distance from the wall. Now, Prandtl assumed that the flow in circular pipe mixing length is proportional to the y. So, the I think Prandtl has just assumed in this way that if it is suppose the proportional to the y, then we can write here L is equal to k y, which k is which is constant and k is a universal constant, it is called. And Nicoradze, from his experimental results, he got this or he suggested the value of this universal constant as 0.4, just by considering L is equal to k y and from the velocity distribution and just matching the equation with the experimental data or fitting the experimental data with that model, and what should be the parameter k, and based on which he has suggested that k should be 0.4 there. Now, other correlations also available for this mixing length. Nicoradze suggested another empirical relationship for mixing length as here L by r, that is r is the radius of the pipe. So, it will be a function of 1 minus y by r, and it is actually empirically related like this 0.14 minus 0.08 into 1 minus y by r whole square minus 0.06 into 1 minus y by r whole to the power 4. This is the polynomial function. So, from which you can calculate what should be the mixing length there. It is a function of just what is that radius of the pipe, and also in the y direction what will be the velocity component there. According to Clark and Flemmer, also this mixing length can be calculated based on these correlations equation number 15. Now, L by r will be equal to some constant of y by r minus r by r to the power n divided by n here. N and c are constants. In this case, n they have suggested n should be 1.3, whereas this c will be actually estimated based on the experimental data, or you just get the dl by dy is equal to 0, from which you can calculate what should be the maximum what is that c value there. So, you have to consider this what will be the c. So, c and n if you know, then you can easily calculate what should be the mixing length by this equation number 15. According to von Karman theory, this mixing length he told that mixing length does not depend directly upon the distance y from the pipe, whereas this Nicoradze or what is that Prandtl, they have suggested that it will be a function of y. But here in this case von Karman they told that their team they told that also it will not be a function of y, but on the distance of mean point velocity in the turbulent flow there. So, as per his assumptions that L should be equal to k into du by dy divided by d2u by dy square. So, in this case if we substitute this L value here, then shear stress should be equal to rho into k square into du dy to the power 4 by d2 u by dy square. So, by equation number 17 you can have this turbulent shear stress there. Now, let us derive or let us having this Prandtl universal velocity distribution based on their mixing length theory. So, in this case we know that du by dy will be equal to what is that this based on this is from equation number 17 we can get here after what is that simplification, this equation number 17 here, this is the equation number 17. So, if we consider here this tau t rho k square, if we substitute this value of velocity gradient after derive, then we can get this one, this equation number 18. Now, owing to the presence of wall a thin layer delta 0 as per this figure shown here, if we developed there this delta 0 and where turbulent mixing is suppressed and the effect of viscosity dominates as shown in figure, then the extremely thin layer is called that viscous sublayer. So, in this case of course, within this viscous sublayer there will be a shear stress that acting whenever fluid will be flowing over this wall surface there. So, if we assume that tau 0 to be the shearing stress acting on the wall, then we can have this tau 0 will be equal to mu into du by dy that will be equal to mu into u by y here in this case. And this y will be considered as that less than equals to delta 0, that is very thin layer of the liquid over this wall surface. And in this case then we can after simplification have this root over tau 0 by rho it will be equal to root over mu u by rho y, that will be equal to v star. So, v star is called as the friction velocity, that is denoted by here in this case by equation number 20. So, after simplification of this equation 19, we are getting root over tau 0 by rho, it is called the friction velocity. So, interesting that whenever fluid will flowing over a smooth pipe at a velocity u, and if we consider the thin layer of distance delta 0 over this wall surface, and because of this viscous effect within this thin layer of the surface there will be some shear stress acting, and this shear stress will be then as per Newton's law that it will be considered as mu into du by dy. Now, this du by dy can be obtained by this mix what is that von Karman theory of this mixing length. Then after substitution of this and if we consider k will be equals to 0.4, then we can have this equation number 20, and it will be called as friction velocity. Now, this equation number 15 becomes mu u rho y, that will be the v star square, which will imply that u by v star, that will be equal to v star y by mu into rho. This will be equation number I think 20. Equation number 20 becomes like this. Equation number 20 becomes like this. Now, substituting at y is equal to delta 0 and u is equal to u delta, that means that over thin layer of this liquid what will be the velocity, that will be considered u delta. So, u delta by v star will be equal to this rho v star delta 0 by mu, then it will be called as Reynolds number based on this thin layer of liquid over this wall surface. So, R e delta is equal to Reynolds number based on the boundary layer thickness delta, it is called. And now integrating this equation number 18 here, we have shown here in this case for this smooth pipe. After integration we can have this equation number 19 here. So, here it is called u by v star, that will be equal to 2.5 ln y plus c, and c is the constant of integration. And after substitution of the boundary condition like y will be equals to delta 0 and u is equal to u delta, then we can have c will be equal to u delta by v star minus 2.5 by ln of delta 0, and after simplification it will be coming as re delta minus 2.5 into ln delta 0. Now, this is the constant of integration. After substitution of this c in equation number 19, then we can have u by u star is equal to 2.5 into ln y by delta 0 plus re delta. As this is called the velocity distribution for the turbulent flow whenever fluid will be flowing over a smooth flat surface. Now, using equation number 17, then we can have u by u star will be equal to what is that 2.5 ln into v star y by mu by rho plus a here. Now, this a is a parameter here, that a will be defined as here in this case after simplification. This a will come here re delta minus 2.5 into ln delta. So, as per this Nicorates' experimental observation, this a is coming 5.5 for smooth pipe. So, very interesting that we are getting this equation number 24 velocity distribution of this turbulent flow whenever fluid will be flowing over a flat surface, the flat surface will be very smooth there. And if we compare this model with the experimental data that is given by research, in that case we are having this model here, these different models here within a certain range. Up to this range here we are fitting this experimental data based on that model here, equation number 22. Then in that case we are getting a is equal to 10.493, whereas this Nicorates says that given a is equal to 5.5. Again here in this case within this range we are getting this y will be equals to what 5.9 x minus 3.094. In this case here we are getting this different a value, and also this for this range also we are getting difference a value corresponding to the constant here 2.5, it will be coming different value like this. So, only thing is that this model based on this Prandtl mixing theory, we are having the almost that means almost a similar trend within this range of experimental condition here. So, in that case a should be equal to 10.493, whereas it will be deviating from the Nicorates' results as 5.5. So, anyway this will be actually obtained based on the experimental data, but this component is coming based on this what is the theory 2.5. So, only thing is that this a will be varying. So, this a depends on what is that Reynolds number based on the boundary layer thickness, and also what is that this one is called the Reynolds number here, and other physical properties of the systems also. So, it is important to know that what should be the velocity distribution in case of turbulent flow whenever fluid will be flowing over the flat surface there. So, you can easily calculate that things from equation number 22. Now, if we apply the boundary condition as u is equal to u max for y is equal to r, the pipe radius, then equation 19 earlier can be solved for Prandtl's universal velocity distribution for turbulent flow in smooth as well as rough pipe also. So, in that case it can be expressed as u max minus u by v star, that will be equal to minus 2.5 ln to y by r, whereas u max minus u, it is called the velocity defect there. So, you have to remember that turbulent shear stress that does not remain constant here and in the central pipe region, but varies linearly as tau is equal to tau into 1 minus y by r. So, equation number 24 you can use for both turbulent smooth as well as rough pipe for this. So, in this case you have to consider what will be the maximum velocity in the turbulent flow. So, that maximum velocity can be calculated from this equation number, provided the value of y, that means from the flat surface what will be the distance, and also what will be the radius. If you are considering the radius of the pipe, then you will be able to calculate what the maximum velocity, and also if you know the maximum velocity, what will be the velocity distribution there. And also Prandtl universal velocity distribution for rough pipes with a roughness height, that can also be considered here. So, it can be derived from the Prandtl's equation that is given in equation number 24. So, based on that, in this case you have to consider that y t, that means up to which the turbulence, that means here turbulent core will be there where laminar sublayer ends, that you have to consider. In that case beyond the laminar sublayer, this distance will be proportional to the pipe wall roughness height. So, it will be equal to C into epsilon. So, C is a proportionality constant. So, using the boundary condition, if we consider that y is equal to u is equal to u, that is y at up to this y t and turbulent core here, and y is equal to y t, that will be equal to C into epsilon. Epsilon is the roughness height, then C is the constant. So, if you substitute this boundary condition, based on this we can have this u by v star, that will be equal to b plus 2.5 ln y by epsilon, and from which we can have this b will be equal to what is that u by v star, u will be y is equal to at y is equal to y t, and then if you are having this ratio, you have to subtract this 2.5 into ln c. So, only thing is that you have to know what will be the proportionality constant, that means if you know the roughness height, then accordingly what will be the height over the surface, if you are considering that turbulent core height, if you are considering, then it will be there. So, y t, if it is suppose 1 into epsilon, then accordingly it will come here, what will be the c value, c is 1 here. So, in that case ln c, ln 1 will be equals to 0. So, this part will be neglected, only b part will be here. So, accordingly if you substitute this b here, so you can get what will be the velocity distribution for the rough pipe. So, Nikodym suggested that this v value will be 8.5 from their experimental results, and for rough pipe in this case epsilon should be greater than equal to delta. So, delta is very thin layer, that means if the roughness height is smaller than roughness height to be considered there. And now, what will be the mean velocity distribution for both smooth and rough pipes? Now, mean velocity to be defined as that is volumetric flow rate upon cross sectional area. So, it will be what is that this if we are having the control volume over that for a small elemental analysis, then after integration of this 2 pi r u r d r and divided by this pi r square, then you can get this mean velocity, where r here will be equal to capital R minus y, this capital R is called radius of the pipe, and dr is equal to minus dy. Now, substituting this, then you can get this v mean velocity will be equal to this, and after substitution of this velocity distribution for smooth and rough pipes, we are getting this velocity distribution here for smooth pipe, and this one is for rough pipe. Similarly, velocity distribution of turbulent flow in pipe based on Blasius experimental results, then Prandtl derived the velocity distribution from Blasius equation. In that case, the Blasius equation is we are having this f is equal to 8 tau 0 by rho u square. So, this will be equal to this after simplification and then it is coming like this. Now, this equation is based on his experimental work on smooth round pipe for turbulent flow, and the parameter f is called the Darcy's friction factor here. So, they have actually got the shear stress that is proportional to the kinetic energy, and based on which they have got this friction factor, that is called Darcy's friction factor. We have already defined in the earlier lectures that what the Darcy's friction factor there, and this Darcy's friction factor, and also this friction factor from this friction factor after simplification or just rearrangement of this equation, then we are getting this. Now, this is applied only up to Reynolds number 10 to the power 5, and now rearranging this equation number 25 here, this equation number, we are getting this tau 0 is equal to 0.0395 rho into mu u to the power 7 by 4 into u by rho to the power 1 by 4 into d to the power minus 1 by 4. Now, with the equation number 20 earlier we have given that we can express this above equation 26 here as u by v star will be equal to this, and or you can express this as equation number 28 here. Now, in terms of this maximum velocity, now because this average velocity is 0.8 times the maximum velocity in the pipe for the range of Reynolds number of 4000 to 10 to the power 5. In this case, we are able to calculate what should be the velocity distribution based on this maximum velocity there. Now, this in this case, as per similarity law, we can write that u by u v star, that will be equal to 8.74 into rho v star u by mu to the power 1 by 7. Now, from this equation number 28 and 29, we can get this equation number 30 as a general equation, like u by u max based on this maximum velocity, that will be equal to y by r to the power 1 by 7, that this is nothing but 1 minus r by r to the power 1 by 7 for circular pipe. So, this power is 1 by 7, that is why it is called the 1/7 power velocity distribution here. So, here how this y and r are related here, in this case the circular pipe is shown. So, based on this we can have this velocity distribution as a 1/7 power law velocity distribution. This is obtained based on the what is that Blasius experimental results. Similarly, the velocity distribution of the turbulent flow in pipe can be obtained from the Nikodym's experimental result. So, as per Nikodym's experimental observation, he concluded that the velocity distribution in the pipe does not follow the Blasius law at all Reynolds number. So, in that case he suggested another expression to express the velocity distribution that obtained from the Blasius experimental results as a generalized form. So, he suggested that the general equation for the velocity distribution will be equal to u by u max, that will be equal to y by r to the power 1 by n. Here instead of 7, here he suggested that it will be n is a constant, this 1 by n that will vary with the operating conditions, and here in the table it is given some results. If suppose 1 by n is equal to 1 by 6, then it will be u by u max should be 0.791, whereas for other values of 1 by n it is shown in the table that we are getting almost that here the u by u max near about to each other, but there will be a variation. So, this because of this 1 by n value, this u by u max will change. So, it may not be only 1 by 7 there. So, 1 by 7 if we consider, we are getting here 0.817, whereas for other values it is changing here from 0.817 to 0.791, 0.806 like this. So, this u by u max changes with respect to n value here. Now, as per Nicoratz's experimental results, that 1 by n, how this coefficient 1 by n is changing with Reynolds number there. It is seen that this power is inversely proportional to the Reynolds number, and the proportionality is that is power is 0.081. So, u by u max should be 0.79 to 0.0865 if the Reynolds number is ranges from 0 to what is the 3.5 into 10 to the power what is that 6. So, so from this graph you can get what is the ratio of velocity to the maximum velocity, and with respect to what is that Reynolds number, and also what would be the power based on this Reynolds number there. So, I will suggest to for further reading this textbook for getting more details. So, in this lecture we have given the concise way of the velocity distribution of the turbulent flow over the surface, and also the what is that through the circular pipe. And this velocity distribution for the turbulent flow is analyzed based on the Prandtl's mixing length theory and also von Karman mixing length theory. Also the generalized equation for this turbulent flow velocity distribution is analyzed based on the what is that Blasius experimental observation and also Nicoratz's experimental observations there. So, that is for all today for this lecture. Thank you.